This video will build on the stuff we've learned yesterday from vectors. First thing we need to do is define what a unit vector is. A unit vector is very helpful to us because it allows us to work with varying different vectors without having to change what we know about the vector. So what a unit vector is exactly what you would think, one unit. So the magnitude of a unit vector is always going to be equal to 1. It gives us a way to represent the direction of any non-zero vector. Any vector we want in the direction of that unit vector can easily be found by basically multiplying by a scalar multiple. We use this letter U to represent a unit vector. So when you see that, usually it's going to talk about a unit vector. So if we want to find v, which is a non-zero unit vector, then the unit vector is going to be 1 over the magnitude of v times the vector v. And so what we say is we want to find that unit vector u, it's a unit vector in the direction of v. So basically, if I said I want to find a unit vector in the direction of v, this is what I'm going to use. I'm going to take the magnitude of the vector v, multiply it by the vector v, and that's going to give me the unit vector. Let's look at an example. Let's say we want to find the unit vector in the direction of a vector v, and then we want to verify to make sure that it definitely has a length of 1, which a unit vector should. So our vector v in component form is -3, 2. Well, we know that in order to find our unit vector, we need to find the magnitude of our vector. So we talked about how to do that last time. So the magnitude of our vector is just going to be the square root of the quantity of the two components squared. So we've got the square root of 13. So we plug that into our formula, and we're basically going to multiply 1 over the square root of 13 times our horizontal and vertical component. If we write this in component form, it's going to look like this. Our horizontal component is going to be -3 over the square root of 13, and our vertical component is going to be 2 over the square root of 13. This would be a unit vector in the direction of vector v, but has a magnitude of 1. Let's verify that it really does have a magnitude of 1. If it really has a magnitude of 1, then when we take the distance of the vector u, we should find that as 1. And in fact, it is. Plugging into our formula to find our magnitude, we see that we get 1. Go ahead and see if you can find a unit vector in the direction of v and verify that it has a length of 1. Go ahead and pause this video, and then when you unpause, I'll show you the solution. Again, here's our formula. Plugging it in, we find the magnitude of our vector v, and our unit vector is going to be a horizontal component of -1 over the square root of 5 and a vertical component of 2 over the square root of 5. Again, you can verify that it has a magnitude of 1 just by simply plugging it in. We have some special standard unit vectors, which we call the vectors 1, 0, and 0, 1. We call them the standard unit vectors because obviously they're standard in the horizontal and vertical direction. To help make this a little bit simpler, sometimes instead of writing unit vectors as 1, 0, or 0, 1, we donate them by the following. So I is going to be our standard horizontal vector, which has a component form of 1, 0, and j is going to be our standard vertical component form, which is going to be 0, 1. So whenever you see this I and j, it's just another way of writing it in terms of the components of the unit vectors. These vectors can be representing any vector. So we talk about vertical and horizontal component. We can rewrite this, instead of saying v1, v2, we can say it as basically the components of those standard unit vectors. So we can write that such that it looks like kind of a statement without the component form, vi, v sub 1i plus v sub 2j. So know that if you see this ij, it's not meant to be super complicated. It's basically taking it and writing it in another form. Instead of writing it in component form, we write it in the standard unit vectors, which we call I and j. Also, you'll hear the book call this as a linear combination. So if it says find the linear combination, they're asking you basically to write your solution in terms of this I and j unit vectors. So here's an example you might see. Let's say we want to write our vector v, which is in component form of 4, -3, as a linear combination of I and j. This is not meant to be super complicated. It really is simply just 4i minus 3j. Again, because our vertical component is going to be -3 and our horizontal component is 4. And we know that we multiply I, which is our horizontal component, and j, which is our vertical component. So if we see this in the standard unit vector, and we see this obviously written in this linear combination, we know that a and b are the horizontal and vertical components respectively. So know that in either form, you'll be able to find the horizontal and vertical component. Let's talk about the direction angle. Another way, or a more specific way, to find the direction of a vector is to talk about the direction angle. That's obviously going to be the angle that we have that our vector makes with the positive x-axis. So you can see a little angle inside here, theta. This is our direction angle. And of course, if you think about it, it makes sense when we talk about the magnitude of our vector. So here's our vector v. The magnitude of our vector times the cosine of this angle would give our horizontal component. And the magnitude of our vector times the sine of that direction angle would give us our vertical component. So using trigonometry, we can see, like we just said, the vertical component and the horizontal component are going to be based on that direction angle. So if we wanted to find, say, for example, the horizontal component of a vector, we just take the magnitude of vector v and multiply it by the cosine of the direction angle. And the vertical component is just simply going to be the magnitude of vector v times the sine of that direction angle. And if we write it in the form of a linear combination, you'll see something that looks like this. So let's do an example. Let's find the components of the vector v with a magnitude of 6 and a direction angle of 115. Well, if you were to draw this, just to kind of see what quadrant the vector would be in, obviously we're going to have something in the second quadrant. This is helpful to know because we know that when we go to draw this, we know it's going to be the second quadrant. When I go to write my solution in component form, I know that I should have a negative horizontal component and a positive vertical component because of the quadrant that it's in. This is a helpful way to check to make sure you've done it right. So our magnitude of our vector is 6 and our directional angle is 115. So plugging into our formula, we can find our linear combination of our vector v. So 6 times the cosine of 115 degrees and 6 times the sine of 115 degrees will give us our horizontal vertical component. So plugging this into our calculator, make sure we're in degree mode, we get an approximation of about negative 2.536 as our horizontal component and 5.438 as our vertical component. Again, it makes sense that we have a negative horizontal component and a positive vertical component because we have a graph of a vector in the second quadrant. So how do we go backwards and take our our vector, and find the direction angle of that vector? Remember, knowing which quadrant it's in is really important. That's going to help verify our answer. We know that the angle is going to be in quadrant 1 because we've got a positive value of our horizontal and vertical component. So make sure that the angle that you finally get in your answer should also be in quadrant 1. Well, if we draw this out, obviously it's going to look like this. Here's our directional angle we're trying to find. And basically, plugging this in, this is kind of what we have. We've got the magnitude of u, and we can find that because we know vector u, and then we need to find the directional angle, which is the theta. So we can do one of two things. We don't have to do both of them. We really only need one of these two components to help us answer this question. Well, obviously, we also need to start with our magnitude of our vector is going to be the square root of 13. Then we can decide, okay, so we've got a vertical and horizontal component. Either one of these is going to help me find the angle theta because it's the same no matter what. So pick one of the values and work with it. Let's say we decide to start with our horizontal component. Well, if our horizontal component is 3, then 3 equals the square root of 13 times the cosine of theta. We can basically solve using our inverse cosine function to find out what theta has to be. And we find out it's approximately 33.69. Remember, it was in the first quadrant, so this would be our final answer. Do be really careful, though, if you have a problem, for example, that you have another component other than, or another quadrant other than the first quadrant. Remember that inverse cosine is restricted between the first and the second quadrant. So if your angle should be in the third or the fourth, remember that you have to do a little bit of math to find that final angle. You can also see why using the cosine or the horizontal component is actually going to be nice because inverse cosine restricts to the first and the second quadrant. If you know that your vector is going to be in the fourth quadrant, it might be easier to do the sine one because we know it's restricted to first and fourth for the inverse sine. Again, another way that you can do this is just thinking about the fact of the tangent. We know that if we look at our vector in terms of its vertical and horizontal component, the inverse tangent of our vertical component divided by our horizontal component is also going to have a direction angle. Again, just be careful that your final answer is in the quadrant it should be. The biggest mistake that students make is they just find the answer by doing their inverse trig function and then don't think about the fact, oops, it's supposed to be in another quadrant, I need to add or subtract something. So make sure your final answer should be in the quadrant it should be. So your exit slip for this video is to come in with the following two problems completely solved. We want to find the direction angle and the magnitude of the vectors below. Here's your first one that you're going to need to find the direction angle and the magnitude. We've got our component form of -3, 4. Which quadrant is this vector going to be in? The second quadrant. So make sure that your directional angle is also in the second quadrant. Here's your second problem. Again, find the magnitude and direction angle of the vector positive 2, negative 4. Which quadrant is this vector going to be in? The fourth. So again, make sure your final answer is in the fourth quadrant. So find these two, direction, angle, and magnitudes, and bring them in tomorrow. We'll go over those as our first thing for our answers.